Evening, ladies and gentlemen. You are warmly welcome to the Institution of Engineers Sri Lanka, and very happy to see you in this evening with another public presentation conducted by the Civil Engineering Sectional Committee of the Institution of Engineers Sri Lanka. I think we have done many public presentations during this tenure with the start of last November, 1st of last November. I'm Engineer Manjula Samarasinghe. I'm the secretary to the Civil Engineering Sectional Committee of ISL. And ladies and gentlemen, I would like to formally welcome you in this evening on behalf of the chairman of Civil Engineering Sectional Committee, Engineer Professor Tishan Jayasinghe. You all are welcome to this presentation, and happy to see such a large crowd in this evening. And today, I especially welcome our presenter today, Engineer Dr. Narinda Silva. And today, ladies and gentlemen, we are discussing on a very important topic, design of shallow foundations as per EC7. Ladies and gentlemen, in this webinar, in this presentation, we are discussing how the EC7 design philosophy relates to the foundations guideline for conducting geotechnical investigation for foundation design in accordance with EC7. Selection of characteristic material, properties for soil, and design verifications in accordance with the three design approaches proposed in EC7 will be explained with example today. So for this, to honor this presentation, the Civil Engineering Sectional Committee invited a very special person. He's a senior lecturer at the University of Moratuwa. I would like to tell you something brief about him, the presenter today. He graduated from University of Moratuwa in 2001. Then he obtained his master's degree in 2004 at the University of Tokyo, Japan, and PhD in 2008, University of Tokyo in Japan. He's a chartered engineer and a corporate member of the Institution of Engineers Sri Lanka since 2011. He's a member of Sri Lankan Geotechnical Society from 2009, member of International Society of Soil Mechanics and Geotechnical Engineering since 2009, and he has published many research publications. And he's really a resource person for geotechnical engineering side. And he has done a great job to the development of this area. And ladies and gentlemen, without taking much time, I would like to invite today the presenter, Engineer Dr. Narinda Silva, to continue the presentation. Dr. Narinda.
Thank you very much, Engineer Manjula, for your very kind introduction about myself. So, without wasting much time, I would like to quickly move to my presentation today. I hope you can hear me. I'm audible and clear enough. So, can I have a verification? Am I audible enough?
Yes, it is very clear. Some small noises come. Now it's okay.
Okay, right. So I will close my video.
Dr. Narinda, with noise coming?
I think it's due to the fan, I guess.
Okay, right.
Yeah, small noise. I will switch off the video because of the connection speed and disturbance. Okay, I hope you can see my screen. Okay.
Yes. Yeah.
Right. So today I am going to discuss about the application of EC7 for shallow foundation design. There I would like to discuss about a few aspects. That is how to select the material properties, for the design, geotechnical investigation, how to conduct geotechnical investigations as per the guidelines given in EC7, the design approaches, and I would like to discuss towards the end of the presentation, I would like to discuss about 3 design examples of design of shallow foundations under various loading and subsurface conditions as per EC7. So I think you are quite familiar with this diagram. This is the Eurocode family, and in 1997 EC7 has been introduced for geotechnical design. The objective of introducing geotechnical design is to kind of bring all the design frameworks into a common platform. That's the idea of geotechnical EC7. It is quite different to the previous design approach used in the design of geotechnical structures. The main difference is that it uses the limit state design philosophy. I will explain about the limit state design philosophy in detail in the coming slides. So, so EC7, as I said earlier, the Eurocode 7 is based on the limit state the design philosophy. So the previous the design approach, the approach that we are quite familiar with is called the working stress method. In the working stress method, the resistance is calculated, estimated, and a factor of safety is applied to obtain the allowable stresses. But in the limit state method, the design approach is different. So material parameters and the we call loads in EC7 as actions. That is the terminology used. The actions are given a proper weightage by applying partial factors for permanent loads or permanent actions. Variable actions are given different weightage by applying partial factors, and the loads or actions are increased by using the partial factors. Then the resistance, in the calculation of the resistance, for example the bearing capacity, the material parameters are reduced by applying partial factors. Again, the factored material parameters are used in a calculation model or the equation to obtain the design resistance. So design resistance is compared with the design we call the effect of actions. Effect of actions is like the combined load, okay, factored and combined load. So these two are compared in the limit state method. So it's different to the previous one because there we use it's quite straightforward. We apply a global factor of safety here, but here in the limit state approach the several partial factors are introduced in the design. Then we have to check for the serviceability limit state, the settlement calculation, particularly in case of in the design of shallow foundations. The deformations are evaluated at the working loads, the unfactored load, and it is compared with the limiting or allowable the deformation. So the limit state can be verified by different methods. The design by calculation, prescriptive measures means for some typical cases we can define typical foundations, typical sizes and so on. So if we can identify that the subsurface fall into a particular already prescribed category, we can define a prescribed foundation which is already designed to satisfy the limit states. So that is what is meant by prescriptive measures. Then there are experimental models and the observational method. So in this lecture today I am going to mainly discuss about the design by calculation, because that is the method that is being used in the design offices. Right. So the general procedure again is explained in this diagram. So you can see the various actions, or we can say loads, acting on foundations or any geotechnical related structure like retaining walls or piles or so on. Then the ground properties are there and the dimensions are there. So sometimes we have to modify the dimensions before using the dimensions in the calculation model. Then the actions, material parameters and the dimensions all go into the calculation model, right? And there we can verify we have to verify the limit states. The limit states there are few limit states. Loss of equilibrium, it's called the EQU or equilibrium limit state. Structural and geotechnical limit state. This is what we are going to discuss today. This loss of equilibrium comes under the overall stability. Then in addition to that, uplift and ground heaving also there. For structural and geotechnical limit state, there are three design approaches. Three design approaches are given in the EC7. The selection of the design approach is the choice of the country. Okay, I'll come to this later. So in simple terms, this is what is happening inside in the design of shallow foundation. So with the shallow foundation is subjected to variable and permanent actions. There can be accidental actions as well, like impact loads. So the weight of the foundation and the soil above the footing, above the foundation, should be taken into consideration in addition to the imposed actions. So these actions, right, all the actions, the weight of foundation, weight of soil and the imposed the actions, all are given the relevant partial factors. The loads are being increased to obtain ED, what is called as ED. I will be using this term frequently through this lecture, to obtain the design effect of actions. Then we have to characterize the ground. Characterize the ground and obtain the design material parameters. Okay, the design material parameters. The first we have to obtain the characteristic material parameters. After characterizing the ground, then apply partial factors to obtain the design material parameters. These design material parameters are used in calculating the design resistance, and these two are compared. And depending on how the partial factors are applied, right, there are several proposals for the application of different partial factors, for the selection of different partial factors. Three different approaches, design approaches, are given in EC7. So in addition to the weight of the foundation, weight of the soil, if the groundwater table is above the base of the footing, then the uplift also should be given the consideration. The uplift force acting on the foundation also should be given the due consideration with the appropriate partial factor. There is a very important principle called single source principle in EC7. According to the single source principle, the pore water pressure, right? Pore water pressure is a favorable action when it comes to the bearing capacity check. Right, it will reduce the bearing stress, the uplift. but according to the single source principle, it has to be considered as an unfavorable action for water pressure. If whatever the stress is coming from a single source, it has to be given a single partial factor. That is the condition given in the proposed in the EC7. So we can't use the same force as favorable for one calculation and unfavorable another calculation. That is not allowed according to the single source principle. So these are the actions, or you can say loads, different kinds of loads that are applied on foundations. The weight of the soil, rock and water, earth pressure, and so on. There can be seepage forces, charge loads, then mooring forces, like lateral loads, traffic loads, the temperature effects can be there, then the movement due to degradation, dispersion, decomposition, self-compaction and solution of material. There can be freezing and thawing induced loadings. Down drag means the negative skin friction in piles. So there can be so many actions. Right. So as I have explained, there are 5 limit states to be satisfied: the equilibrium, the loss of equilibrium of the structure. Then comes structural and geotechnical, the limit state. The structural means internal failure or excessive deformation of the structure or structural elements. Geotechnical means failure or excessive deformation of the ground. So these two are taken together in the design of shallow foundations. So in addition to that, we have uplift, uplift coming from the buoyancy forces. Then in addition to that, if the foundations are, say you can think of a deep excavation. If the foundations are constructed at the bottom of a deep excavation, there can be heaving, hydraulic heaving, piping and so on, the hydraulic related failures. So we have to consider those aspects as well. So in addition to these, the overall stability, particularly if the foundation is resting on a sloping ground, the overall stability should be checked, and the serviceability limit state also has to be checked for all the geotechnical structures. So the design of calculation, it's all about the loads or actions and material properties. As I have explained, the material first we have to obtain the characteristic loads. Then we multiply by the partial factors and obtain the design actions. Similarly, we modify the material parameters to obtain the design material parameters. Dimensions also have to modify in some cases, mainly for retaining structures, and for foundations subjected to eccentric loads, we have to modify the dimensions. I'll come to this with an example later. Then we obtain the resistance and compare the resistance with the design effect of action. So we can call this as the combined load, total combined load. For design verifications, there are 2 parameters. One is called over design factor, that is RD over ED ratio. Tau, it's given by tau. Then the degree of utilization, delta, it's the reciprocal, 1 over tau, ED over RD ratio. Okay, we after we calculate RD and ED, these two can be calculated and the design verification can be made. The over design factor for a satisfactory design, the resistance must be larger than the effect of action. So this tau value must be greater than 100%. The delta value must be less than 100%. So for a satisfactory design. There is a comment, please share a link or any feasible connectivity. Is there any connection problem? Can you all hear me?
Yes.
Yes, sir.
Okay, right.
Clearly.
I'll continue. Right. So now let me move on to these partial factors. So these are the partial factors proposed in EC7. I will be coming to this again in the coming slides. We will be repeating the same with the examples as well. So for the actions or the loads, these A1 and A2 partial factors are proposed. So you can see two different sets, one for permanent actions given by G, gamma G, and variable actions, gamma Q. And again, the permanent and variable actions are categorized into favorable actions and unfavorable actions, right? At the top you can see unfavorable, at the bottom favorable. So gamma G means unfavorable. So unfavorable means if we are interested in estimating the bearing resistance, right? If the whatever the applied action is unfavorable for the bearing resistance, bearing capacity, then we have to select one of these factors in increasing the load or action, right? If some action is favorable, that means it tends to reduce the applied action, then we can think of using gamma G favorable. Similarly, for variable actions also, gamma Q favorable and gamma Q unfavorable. This top one is unfavorable. The partial factors are proposed, right? Then there are two sets of material properties, M1 and M2, partial factors for material properties M1 and M2. This is the top one is for the friction angle, the drain friction angle or effective value, then effective cohesion. The unbrained cohesion, if we are going to carry out the bearing capacity check for clay type soils, the unbrained parameters are used. So in such case, the partial factors for unbrained cohesion are given here. The unconfined compressive strength, in case of rock, the unit weight of soil is unfactored. Okay, you can see that the factor given is 1. Then the last three are the partial factors for the resistance. Once you calculate the resistance, bearing resistance, the resistance must be divided by the R1, R2 or R3 depending on the design approach. We have to select the appropriate R, and the resistance has to be divided by one of the partial factors for resistance. So for bearing resistance, if we are estimating the bearing resistance, these are the partial factors, okay, proposed. For sliding, if the foundation is subjected to lateral loads, then we have to check for sliding. These are the partial factors proposed for sliding. Okay. Other factors are not relevant for shallow foundations. They are this is for retaining structures, and this is for anchors. So you can see that there are two sets of partial factors for actions, two sets of partial factors for material properties, and three sets for resistance. So different design approaches propose different sets. And this is actually not relevant, although I have included it. It is for the design of pile foundations. You can see the partial factors for resistance are different to that of shallow foundations. For this one we have only 3 partial factors for resistance, but for pile foundations there are 4 sets of partial factors proposed for the resistance. Right. So these are the 3 design approaches. You can see in the top row, design approach 1, this is 1 means the design approach, 2 and 3. In design approach 1 there are 2 combinations. So if we are following design approach 1, then we have to check both combinations, right? Then the A1 partial factor set for actions, M1 partial factor set for materials, and R1 partial factor set for resistance should be used in the design approach 1 combination 1, right? Similarly, M2, A2 and R1, M2, A2, R1 are given in the previous slide, if you remember this, right? M2, A2, R2 should be used in design approach 1 combination 2. This general one is the relevant one for shallow foundations. Okay, this is the one relevant for shallow foundations and earth retaining structures. For both, these general ones are relevant. Then for design approach 2, A1, M1, R2 and A1 or A2, there you can see some sign, star sign and a cross sign. I will explain this later. One of these has to be used, M2 and R3. So A1 and A2, you can see that in design approach 3, both A1 and A2 are A1 set of partial factors and A2 set, both are proposed. So this star means for structural actions, right? If the action is due to some structural load, then A1 set should be used. If it is due to some geotechnical load like the backfill also, then the partial factor relevant for partial factors corresponding to geotechnical action should be used, A2. So, okay. I'll be explaining some examples worked out using all 3 design approaches. Then I will be explaining these differences in detail, right? Okay, right. So the 3 design approaches are explained again in detail. You can see for design approach 1, all the factors are given here, right? Here only the set A1, M1, R1 set is mentioned, but here the factors are also listed. So these are the ones, the red, the area marked by the red rectangle, the partial factors given in this region should be used for design approach 1 combination 1, and these are the factors for design approach 1 combination 2, right? And if you carefully go through these partial factors, you can see that in design approach 1 combination 1, permanent and variable actions are increased, but material properties are not increased. They are basically unfactored. Okay, the same concept is explained here. You can see that these are the representative actions. Okay, unfactored loads you can see, and this is the partial factor for variable actions, partial factor for permanent actions. So loads are increased, and this is the the effect of action, right? Effect of action means the total load factored. Material parameters are unchanged. No factors are being used. Then in the second approach, you can see both the actions and the material parameters are factored. So the permanent actions are unfactored, but variable actions are factored. The design approach 1, combination 2. Material parameters are factored. So you can see that on the material side, in design approach 1, combination 2, in the material side, material parameters are reduced and loads are increased but slightly compared to this one, because you can see that only the variable actions are increased, not the permanent actions. So loads are slightly increased, material parameters are significantly reduced, and we do the design check. The same principles are explained using an equation, using equations in the bottom left corner. G means permanent actions, Q means variable actions. So variable actions, there can be several variable actions. So this QK1 means the primary variable action, and these are called the accompanying variable actions. Mean if there are more than one variable action, everything sigma QKJ represents everything else, right? So all the variable actions you can see are multiplied by 1.5, right? This is the factor 1.5. Permanent actions are multiplied by 1.35. This is the design approach 1, combination 1 equation. So material, all the loads are increased, but material parameters are unchanged, unfactored. This F means whatever the bearing capacity equation, and this whatever you see, the value you see at the denominator is the partial factor for resistance. You can see that at the bottom, partial factor for resistance is 1. So this is also unfactored, right? This F is the function for bearing capacity estimation. Then the design approach 1, combination 2 on the right hand side, can see permanent actions are unfactored, they are multiplied by 1. The variable actions are multiplied by 1.3, this value. Material parameters are reduced, right? Tan phi, this is the characteristic friction angle, it is reduced by it is divided by 1.25, and the cohesion is also reduced. Then the reduced values, or we call them the design values, are used in the whatever the bearing capacity equation. Then once you obtain the resistance, you have to divide it by the partial factor for resistance. Again, the partial factor for resistance is this, it's 1. Okay, that's the idea of these two approaches. I hope you have a clear idea of design approach 1. Similarly, design approach 2. Design approach 2, you can see both permanent actions and variable actions are increased. Material parameters are unchanged, but the total resistance is divided by 1.4. This is like a global factor of safety. You can see if in the estimation of bearing resistance, it is divided by 1.4 here. Material parameters are unfactored, right? And permanent actions multiplied by 1.35, variable actions multiplied by 1.5, right? And the total resistance divided by 1.4. Yeah. Okay. So the same philosophy is explained by using this illustration. You can see that the loads are increased. Okay. Material properties are unchanged, but once you obtain the resistance, it is reduced, right? The factor is applied here, and then the comparison is made. So I hope it's clear. There's a question: accompanying variable actions are also reduced by the reduction factor. Where it's not reduced, it's increased. Okay, increase, yes. Design approach 3. This is the this is design approach 3. Wait. So let me explain it by using the governing this equation. You can see that for structural actions, these are the permanent structural action, variable structural actions, right? Structural actions like weight of the foundation, and if some surcharge is coming from a structure and so on. So those are all called structural actions. If you are not quite sure about what to be used, it's always conservative to assume whatever the action as a structural action, because higher partial factor is used for structural actions, right? 1.5. So the permanent structural actions are multiplied by 1.35 because A1 set is used, right? This one 1.35. Then the variable ones are multiplied by 1.5. All are unfavorable because we are interested in the bearing resistance. Then geotechnical ones, these are the geotechnical actions. If there are any geotechnical related actions, okay, you can see that permanent geotechnical actions are unfactored, multiplied by 1. Variable geotechnical actions are multiplied by 1.3. So this is the primary one, accompanying one, if there are. Okay, then we will obtain the total, and the material parameters are also factored. Okay, you can see the partial factors. For friction angle, 1.25 is used. For undrained, if you are using undrained cohesion, 1.4 is used. Then the bearing capacity equation is used to obtain the bearing resistance, and the total resistance is divided by the partial factor for resistance, which is equal to 1. Okay, this is the one. Partial factor for resistance is equal to 1. So I hope now you have a clear idea about the 3 design approaches. The selection of the it's a national choice. Whatever the design approach for the design is a national choice, and you can see in Europe the selection of different design approaches by different countries, right? In UK, so we have been following BS codes. In UK they are using design approach 1. Okay, so in design approach 1, the calculations are a bit complicated because you have to check for 2 combinations, combination 1 and combination 2. Okay, so in addition to the bearing resistance, there can be some other the limit states like loss of stability. This bearing is the one that we have been talking about. Sliding, there can be structural failure. Okay, and there can be a combination of structural and geotechnical failure. So these are the different types of the limit state for shallow foundations. Some guidelines are given for geotechnical investigations related to shallow foundations. The guideline given is the depth of investigation below the bottom of the shallow foundation footing should be the greater of these two, right? These are for strip or individual square pad footings. You can select the largest say for example anticipated footing width 3 times the width or 6 meters, right? Whatever the largest value, the greater value should be used as the minimum depth of investigation as per EC7. for raft foundations 1.5 times the width, right? If a raft foundation is anticipated, at least the investigation shall be carried out up to a minimum depth of 1.5 times the width of the raft. So that is the guideline given. If a rock or a competent strata is encountered, that becomes the limiting depth for ZA. We can terminate the investigation there, right, at the very hard straight rock. Then this is not available in EC7, but I just include it to give you a guideline on the interval of investigation points, the borehole location. Any question? Okay. So for high-rise and industrial buildings, the spacing can be spacing between boreholes can be 15 to 40 in a grid pattern. It can vary between 15 to 40 meters depending on the importance of the structure and the extent of the structure. Okay. So this I have already explained. It's like a summary of what I have already explained. How to estimate the design effect of actions and how to calculate the resistance, right? I have already explained this, so I will skip this for the moment. Right. So in EC7, for the estimation of the resistance, I told you that there is a F into material parameter. This F is the bearing capacity equation. So in EC7, these two equations are proposed. For unbrained condition, that means if the foundation is constructed on clay subsurface, right? If we are interested in the short term the behavior of the foundation, we have to do the check for the short term condition, then unbrained parameters must be used. This is the appropriate equation, right? The resistance R over A dash, this is the effective area, is given by this particular equation. You can see this is the design undrained cohesion Cu value, and BC, SC, IC are, right, the base inclination modification factor if the base is inclined like this. If base is inclined at an alpha to the horizontal, then we have to calculate this base inclination factor, base inclination modification factor. Then SC is the shape modification factor. You can see 1 for rectangular shape, another value is given for a square or circular shape, SC value. Then comes load inclination modification factor if the load is inclined to the vertical. That means if both vertical and horizontal loads are applied, the resultant will be inclined to the base. So in such case, you have to calculate this IC term as well. Okay, this H is the horizontal load, and this Q is the overburden pressure at the base level. Overburden pressure, total stress, right? Total stress, total overburden pressure at the base level. Then the second equation is for drain condition. If the foundation is resting on like C5 soil, like laterite, or sandy subsurface, then we have to check for the drain condition, and this is the equation proposed. It's quite similar to the Wessex bearing capacity equation. You can see there are three terms: C term, Q term, and a gamma term. This is the resistance coming from cohesion, the resistance coming from the depth or overburden. Third term is the resistance coming from the unit weight or the width, right? Gamma term, it's called the gamma term. And again you can see the base inclination factor, shape shape factor, and the load inclination factor, BC, SC and IC. Okay, and the relevant equations are given here. I am not going to explain them in detail. So if you are using say for example load inclination factors, this IC, IQ and I gamma, if the load is inclined, we have to calculate IC, IQ and I gamma. Others are very straightforward. There we have to estimate a parameter called M. The guideline for the estimation of M is given here. If the horizontal load, whatever the resultant horizontal load, right, is acting only in the direction of B. For example, let's say this is the footing, this is your B direction, your horizontal force, resultant horizontal force is acting like this. Then calculate M as MB using this equation. If your resultant horizontal force is acting in the L direction, this direction, right, parallel to L, then calculate M as ML, it's given by this. Okay, and if the resultant horizontal force has components in both B and L direction, like this, if the resultant horizontal force is like this, then you have to calculate M using the equation given at the bottom. You will need both ML and MB in that case, in such case. Okay, and you can see B dash L dash. This B dash L dash are called effective dimensions, right? Effective dimensions in case if the load is not applied concentrically, if the load is applied with a certain eccentricity like this. Okay, so this is the column. Column must be say at the center, but the column is subjected to a vertical load and moments, both in B and L directions. There can be moments. These moments can be replaced by eccentricities. So this is the point where the load is applied after applying the eccentricities. So once this point is selected, the effective dimensions can be calculated. The effective width is taken as the this is the new point of action. So from this point to the closest edge of the footing is this, right? So this is taken as half of B dash. Similarly, the distance from the line of action to the other edge, right, in the direction of L. So this is taken as half of L dash. Then we can calculate the effective area of the footing. This is the effective area of the footing. So it's given by B dash is equal to B minus 2 times EB. B is the width, original width. L is equal to L dash is equal to L minus original length minus 2 times EL. EL and EB are the eccentricities. Okay. So the eccentricity should not exceed 1/6 of the width of the footing to avoid the negative stresses under the base. Right? If it's a circular footing, it is recommended in EC7 that the eccentricity should not exceed 0.6 times the radius of the footing. So those conditions are to be checked, right? Then I would like to briefly discuss about ground characterization. So to obtain the material properties, we conduct tests. Then from the test we can derive the derived values of geotechnical parameters by using equations or empirical correlations. We can obtain these derived parameters. Then if there are so many tests, we can do the characterization and obtain the 95% confidence value, that is called characteristic value. Okay, the 95% confidence values of the parameters can be obtained. Then those values are the characteristics values are factored, and the design values are used in the design equation, whatever the bearing capacity equation, right? So different in the part 2 of EC7, the guidelines for conducting different the tests are proposed for CPT, SPT, dynamic probing, weight sounding, flat dilatometer and plate loading test. So these guidelines are given. I am not going to go into the details of these tests because it's out of the scope of this lecture. But if you are interested, you can refer to these guidelines. Now the thing is, this characterization, in order to do this characterization, to obtain the 95% confidence value, lot of test results must be available, right? So the derived values can be obtained. I will give you some very commonly used the tests and they are how to obtain the parameters from those tests. The Vane shear test is widely used to obtain the undrained cohesion of clay type soils. This is the equation used with the dimensions of the vane. Okay. Then comes the standard penetration test is widely used for undrained cohesion. This Stout and Butler correlation is widely used. This is an empirical correlation. Cu over n values are plotted against the plasticity index, and you can see in most of the design offices we are using Cu over n equals to 5, right, as the empirical correlation for obtaining the undrained cohesion of clay. Then please keep in mind that this Cu value is the derived value, right? Similarly for CP, the cone penetrometer test, Su is identical to Cu, it's the same. This equation is used. Okay. The friction angles can be estimated using these guidelines are given in EC7. Friction angles can be calculated using the standard penetration test results. So 30 is taken as the base value, right? Then depending on the angularity of the particles and the grading, we are adding degrees, right, as given here. Plus depending on the SPT n value also some guideline is given for adding some value. So it's the summation of everything. Then this is called the constant volume angle of sand. Constant volume angle of sand and gravel. So constant volume means when you shear sand, right, it dilates, the volume increases and then comes to a constant volume. So at the constant volume shearing, the friction angle is less than the peak of the friction angle. So the constant volume friction angles are given by this. Okay. So for clay soils, this is another empirical correlation. For purely clay soils, the drain, the friction angles, again constant volume. So in addition to that, we can use CPT test for obtaining the friction angle, and this is for friction angle again. Then the E values, the stiffness values, elastic modulus values also can be calculated using the CPT correlations. There are so many such correlations for SPT as well. Okay, so then how to get the characteristic value? All the test methods that I have discussed are giving the derived values of geotechnical parameters. So from the derived values we have to obtain the characteristic values. So one the most appropriate method or the recommended method is to carry out a statistical analysis. If you have a lot of data, then obtain the 95% confidence value as the characteristics. But in Sri Lanka we know that we don't do lot of laboratory or field tests. So then the only option available would be this, the cautious estimate. This is where the experience comes into play. Okay, so from the derived values we cautiously estimate the characteristic values, and these values are factored. Okay, so now I would like to explain few design examples. This is a very typical straightforward case where you have a rectangular footing 1.5 meter by 2.5 meter. Let's assume that the foundation is placed at a depth of 0.5 meters. The imposed loads are given here. The imposed variable action is these Q loads actions 450 kilonewton. Permanent action is given by 800 kilonewton. So we have to consider the weight of the footing and the weight of the soil above. If the water table is here, we have to even consider the uplift also. That is what is given in the in these two notes. Right. So then we are asked to do the design check. The material parameters, the characteristic values are given here. Okay. From the derived values, characteristic values are cautiously estimated and they are given here. The characteristic unit weight, this is the concrete characteristic unit weight. The friction angle, characteristic friction angle 35 degrees. Cohesion is taken as 0, it's sandy soil. Then the unit weight of soil 18. So nothing is mentioned about the water table, so we assume that the water table is well below the bottom of the footing. Then we are going to use the design approach 1 first. Right, design approach 1, and these are the relevant parameters to be used. You can see that all the actions are unfavorable against the bearing capacity. So unfavorable partial factors are going to be used. Those are the ones marked by these dash squares, okay, dash rectangles. Parameters to be used for combination 1 and combination 2. Right, now let's do the calculation. First we have to estimate the design effect of actions, or we can say the design total load in simple terms. The characteristic self weight, I told you that the self weight has to be calculated, the self weight of the footing and the self weight of soil. Since this depth is 0.5 meters, right, in this calculation it is assumed that the entire region above the base is concrete. So 1.5 into 2.5 into 0.5 is multiplied by the characteristic unit weight of concrete here. Gamma CK is the characteristic unit weight of concrete. LBD are this is the volume of the base and the soil above. So characteristic self weight of the footing is calculated, including the weight of soil. Okay. So this is not a bad assumption. It's conservative. Then the partial factors are estimated. You can see two values, the design approach 1 and design approach 1, combination 1 and combination 2, okay, are both done at the same time. So you can see within this bracket you can see two values. The top value is for combination 1, bottom value is for combination 2. Okay, so for combination 1, 1.35, 1.5, right, you can see 1.35 for permanent actions, 1.5 for variable actions. Similarly for combination 2, right. So with that we can calculate the total vertical action, or we can say design vertical action, VD, calculated by weight of the, this is WGK is the weight of the foundation and the weight of the soil, right, plus this VGK is the permanent imposed action, right, permanent imposed action. These two are multiplied by 1.35 gamma G, this one for combination 1, it is multiplied by 1.5 for combination, this is for variable actions, 1.5, 1.35 and 1, this. Then the imposed variable action, this VQK, that is 450, is multiplied by gamma Q, these two values. Okay. Then the two values are given here. The design vertical actions for combination 1, combination 2. Okay. So then we can estimate the QED value, the resistance, the design bearing pressure, or the total effect of actions divided by the area, effective area of the footing. No eccentricities are given, therefore we divide these two values by the area of the footing and you will get these two. Okay, now let's calculate the bearing resistance. The characteristic material properties are given here. Okay, for combination 1 you have to use M1 partial factors for material to obtain the design material parameters, M2 for combination 2. So M1 and M2 are given here, the relevant parameters for friction angle, for cohesion. Okay, cohesion is 0, so you don't have to worry about the cohesion. Friction angle, of course, you have to whatever the tan characteristic friction angle should be divided by 1 for combination 1. It should be divided by 1.25, this one, for combination 2. So those are the design friction angle values. The design cohesion is 0. Now everything has been calculated. We can do the check. Bearing capacity factors are given in the EC7, NC, NQ and N gamma. Actually NC will not come because the C term is 0. So NQ and N gamma should be calculated using the design friction angle, right? So we have two design friction angle values, one for combination 1, one for combination 2. So you will get these two NQ values. Similarly N gamma values. Shape factors again, right? These are the values, the equations proposed in EC7. So depending on the design friction angle, you are getting two different shape factors for combination 1, combination 2. SC, SQ, SCAP calculated. Okay. Then in the equation to calculate the bearing design resistance, we have C term, Q term and gamma term. So Q is the overburden pressure, design overburden pressure. The overburden pressure is calculated by multiplying the unit weight of concrete gamma into whatever the depth of the footing. This is 0.5, this is 18. 18 into 0.5 is 9. Okay. Once you obtain the resistance, it has to be divided by the partial factors for resistance, which is actually unfactored. It's all equal to 1. Okay. Right. So now you can obtain calculate the C term, Q term and gamma term. The C term from the cohesion, it's 0. SC and C term is 0. From the overburden pressure, this one, you can calculate the Q term, and these are the two Q term values. Similarly, gamma terms can be calculated, and the summation 402.8 plus 0 plus 507 is the total design resistance, right? Similarly, if you take the other summation of the other three, you will get the total design resistance for combination 2, and you have to divide this by whatever the partial factor for resistance, which is 1. It's unfactored, so you are getting the same values. Now we have obtained the design resistance QRD, and in the previous slide we have obtained QED, right? That is the applied load or the effect of actions, total effect of action. These two are compared, and here we calculated utilization factor QED over QRD, right? And this ratio, the utilization factor, must be less than 1. Okay, you can see that for combination 1 we are getting 54%, for combination 2 we are getting 97%. It's less than 1. The design is unacceptable if one of these values is greater than 100%, right? That is the design check. verification. Let me quickly go through the questions if there are. There is a question: what happened when the eccentricity exceeds the limit? Then of course we have to change the base size dimensions to reduce the actions. Others are related to some technical issues. Okay, let me move on. The design approach 2, same example, design approach 2. So I think now it's very straightforward. I don't have to explain this in detail. Only the factors are going to change. Okay, so simply follow this equation. Whatever the permanent actions, including the self weight, multiply by 1.35. Whatever the variable actions, okay, multiplied by 1.5, and obtain the design effect of actions that is given here. Only one value. There is no combinations as such as in the previous case. So just one value will be calculated. So divide by the area of the base, you are getting the design, the bearing pressure. Okay. Then calculate the resistance. So once you calculate the resistance, you have to divide it by this 1.4, like applying a global safety factor, right? And the material parameters are unfactored, so no need to modify the material parameters. I think friction angle, design friction angle is equal to the characteristic friction angle, which is 35 degrees, cohesion 0. So calculate the bearing capacity factors using the design friction angle for approach 2. Then calculate shape factors as before. The C term, Q term, gamma term in the bearing capacity equation has been estimated. Take the summation. This is the summation, total resistance. Now once you obtain the total resistance, you have to divide it by gamma RV, partial factor for resistance, which is 1.4 here, 1.4, right? So this is the design resistance. Now you can compare the design resistance with the design bearing pressure. Okay, and it is 75%, which is less than 100%. So the design is acceptable. There is a question asking whether we are supposed to do all the design checks in Sri Lanka. Actually, we have not yet adapted Euro codes for geotechnical design. Therefore, it is not very clear at the moment, but we don't have to do all 3 design checks. I mean, it's not done in anywhere in the world. There is a national choice. National annex has to be prepared. In the national annex, the clear guidelines has to be given on which approach to be used, and we have to stick to that approach, right? Then design approach 3. Okay, so again it's just a matter of changing the appropriate the partial factors. Okay, I think I can quickly go through this. The only thing I have to explain here is this, the use of set A1 for structural actions and set A2 for geotechnical actions. So we can assume, nothing is mentioned about whether this is a structural or geotechnical action, we can simply use the partial factors for structural actions in the calculation, because you can see that for structural actions the partial factor is larger, right, than the geotechnical. This is, you can see for geotechnical actions partial factor is 1, but for structural actions, unfavorable, permanent, 1.35. For variable ones, geotechnical actions should be multiplied by 1.3, structural actions to be multiplied by 1.5. Okay, so using this, assuming that whatever the action as a structural action is conservative. Okay, so geotechnical action means if whatever the applied load is coming from geotechnical related construction like a backfill, okay, and so on, and if the conditions are certain then we can think of using geotechnical partial factors, right? So that's the only difference, but in this case we assume that all the actions given are structural actions. So apply the relevant partial factors as in the previous example. Material parameters are factored, so you have to again apply the partial factors for material parameters. So 35, this is tan 35 divided by 1.25 now, okay, friction angle. If this is the one, no cohesion, 0. Once you obtain the design friction angle, you can calculate the bearing capacity factors NC, NQ and N gamma, right, and obtain the total resistance divided by this value, okay, partial factor for resistance, which is equal to 1 in the design approach 3. So shape factors and the C term, Q term and the total resistance divided by 1, right? So this is quite interesting. According to design approach 3, as per design approach 3, this design is unacceptable, okay, it's greater than 100%, the utilization factor greater than 100%, therefore this design is unacceptable in some countries where it is acceptable in some other countries, okay, can't help. Right, another example, a bit more complicated. I don't know about the time. Engineer Manjula, can you please
Yes, you can continue. It's okay.
Right. I'll try to finish as quickly as possible, because now I have explained the concepts. I think I can go faster. Right. This is another example with a foundation subjected to moments. Right. And when you calculate the eccentricities only by considering the imposed loads, you are getting 75 millimeter and 100 millimeter, right? So these two eccentricities are simply calculated only by considering the imposed loads, this a permanent one and the variable one, okay. Whatever the moment divided by the vertical load gives this. It doesn't take the weight of the foundation or uplift or anything into account. Therefore, first thing we are supposed to do, if in such case, because these eccentricities are calculated only by considering the imposed loads, we have to modify these eccentricities and obtain the design eccentricities. That is the first thing to be done. So that calculation is explained here, how to obtain the design eccentricities, right? This is the design eccentricity in the direction of B. It is modified from 75. So this is 75 here. You can see that the permanent actions, variable actions are all factored using the appropriate factors, okay. Now sorry, where is design approach 1? Suddenly jump to design approach 1. Yeah, this is design approach 1, huh? So for design approach 1, gamma G, whatever the relevant gamma G and gamma Q values have to be used for permanent and variable actions, and since this EB is calculated only by using the imposed load, right, so you multiply this EB by this one, divide it by the total load, the weight of the footing, the permanent imposed action multiplied by gamma G. This is the variable action, same as this one, right? So weight is taken into account in the in obtaining the design eccentricity in the direction of B. So you can see two values, one for combination 1, design approach 1, combination 1, this is for combination 2. And we have to check for the allowable eccentricity, okay? It has to be less than 1/6 of the footing width. So once you obtain the eccentricity in the direction of B, you can calculate the effective dimensions, B dash. And you are getting two values because there are two approaches, right? Similarly, you have to do the same thing for EL, right? EL. Since it is given only by considering the imposed loads. So these are the factored imposed and permanent loads. Weight is added, weight of the footing is added, right? And these are the design eccentricities. Again, we have to do the check, and the effective length is calculated. Once you obtain effective dimensions B dash and L dash, you can get the effective area of the base. So we need this effective area in obtaining the design bearing pressure, right? Design bearing pressure. So we can obtain the design bearing pressure. This is design bearing pressure is, this is the permanent imposed load multiplied by partial factor, variable load divided by this. You have to take these two as well, weight and the permanent variable action, right? So it's quite similar to the previous calculation, and you can obtain the total load, design load factored, okay? And you have to divide that by the effective area now, not the total area, because of these eccentricities, right? The effective dimensions have been calculated as given here, divided by these two. Now you can get the design bearing pressure. So this is one calculation, and we have to compare this with the design resistance. Then the design resistance, estimation of design resistance is quite similar to the previous one. You have to obtain the design friction angle by applying the relevant partial factor, and these are in the design approach, you can, this is, sorry, in the design approach 1, combination 1, no partial factor is applied, but combination 2 there is a partial factor for material properties. So that is why you are getting two different values. See, estimate NC, NQ and N gamma. Then the shape factors, in the estimation of shape factors, you can see B dash, L dash value, right? So in the previous calculations also it's the same, but in the previous calculation there are no eccentricities, so we use the original dimensions, but now we have to use the correct effective dimensions, and this is the design friction angle. Obtain SC, SQ, S gamma. Then you can obtain the C term. This is the C term, which is 0, Q term and the gamma term. Take the summation, divide it by the partial factor for resistance, right? And now you can do the design verification check, calculate the degree of utilization, okay? So that's about design approach 1. Similarly, we can do the calculation for design approach 2 as well. Okay, the only difference being the change in the partial factors, right? Partial factors are different. The calculation procedure is identical. So I think I can skip this. Similarly, design approach 3, the only difference being the difference in the partial factors, and if there are geotechnical or structural actions, you have to separate and apply separate partial factors, but in this case it's not relevant. All the actions are considered as structural actions, so it's estimation of the design effect of action, design bearing pressure is identical, okay? So the only thing you are supposed to know is this modification to the eccentricity, right? Eccentricities have to be modified by considering the weight of the footing and the factors. Okay. Finally, this is again strip footing on clay type soils. There's another example quite similar to the example that I have discussed. Only difference being the material parameters. Okay, for clay soils we have to use undrained parameters. So the short term is critical for foundations on clay most of the time. So undrained parameters has to be used in the estimation of the bearing resistance. The estimation of the bearing pressure, design bearing pressure, is almost identical to the previous example. Use undrained cohesion, this value, characteristic undrained cohesion, apply whatever the relevant partial factor for this and do the calculation. Now in the estimation of the bearing capacity you have to use a different equation, right? Different equation is this equation should be used. If you remember, in EC7 I showed you in one slide, there are two equations for the estimation of resistance, one for undrained condition, one for drained condition. This undrained one should be used. Then another calculation is if you are interested in doing the calculation using effective parameters, long term bearing resistance of this footing, then we have to use the effective cohesion and effective friction angle, right? Effective values. So if we are using the effective values, we have to take the uplift force into account, because the water table is above the base, right? So it is in this kind of situation, the water table, maybe during the site investigation, water table is observed at a depth of 1 meter. It is always conservative to assume that the water table can rise up to the ground level during the worst case scenario. So assume that this water table is here at the existing ground level and do the calculation. It's always conservative. And the water table applies an uplift force, right? So when you calculate the design resistance, design effect of actions, that is design load, permanent, the imposed permanent action, imposed variable action, weight of the footing, okay, and the soil, and the uplift. Uplift is acting in the opposite direction, so you have to deduct it, right? Deduct the uplift load, but uplift load also has to be factored, right? And it is a actually it's a favorable action. It's a favorable action. In this design example, I took it from a very famous book. They are using gamma G favorable. You can see here, design upthrust. Gamma G favorable partial factors are used, but according to EC7, according to the single source principle, the uplift, whatever the pour water pressure, right, must be considered as an unfavorable action. So when you deduct it, you have to multiply it by unfavorable. Better to multiply it by unfavorable, whatever the factor corresponding to unfavorable action. Okay, permanent unfavorable action. So considering the imposed loads, variable loads, permanent loads, weight and uplift, you can calculate design bearing pressure, right? Design bearing pressure. Then using the drain parameters, you can calculate design resistance by applying relevant factors, calculate design resistance and do the check. Okay, so I think I can stop for today. Engineer Manjula, I think I am done.
Thank you very much, Dr. Narendra Silla. I think it was very interesting, informative, and very practical presentation. We'll invite the participants here to have any questions. If you can raise now, make sure to rename your name to a good name. Some are shown in numbers, and rename your good name and ask any questions.
Dr. Nasvi, I think he has raised his hand. Yes.
Hi, Dr. Nalin. Yeah, I was listening to your presentation. Very interesting.
Yeah, thank
Can
you.
you hear me?
Yeah, I can hear you.
Yeah, actually, this is regarding the single source principle.
Yeah.
We also have been following what actually I did in your example. I agree with what they have done in the example because now single source principle really matters. For example, when we take a slope stability problem, when we use method of slices, depending on the slip circle center, some slices are favorable, some slices are unfavorable. So it really matters. Like we have to apply same factor. But here,
I agree.
what we do is since this uplift thrust is favorable, and also when we have to definitely reduce it from the action, we have to reduce it, and when we apply favorable factor, we are reducing by a lower value compared to single source principle,
Yes,
so
it's
that our resultant action is on the high side and we are on the safe side.
yes, I
I
agree.
think it's not a bad idea to apply the favorable factor according to me.
I
What do you think?
totally agree with you, Dr. Nasvi. Yes,
Yeah,
I totally agree with you. But yeah, I have seen that in some it's a bit confusing. Some
yeah,
in some cases they are using I think they are interpreting the single source principle in a wrong manner. Yeah.
yeah. That's all. Nalin, yeah, very interesting presentation. Thank you.
Thank you, Dr. Nasvi, for your.
Yeah, welcome.
Thank you.
I think Dr. Nawa is also here. Dr. Nawa?
Yeah.
Dr. Nawa.
Yeah. Thank you, Dr. Nalin. Yeah, I also had that. I mean, the single source principle, like people use it in different ways in different calculations.
Yes.
Like if for example, for a sheet pile walls, if the water is on the active side and the passive side, consider that both are water pressure. So we consider single source.
Yes.
Now, in terms of this retaining wall, where the water comes with the soil weight, the saturated weight, and the uplift comes as again like just a water pressure. So it's not like it's a water. It's like a soil weight versus the water pressure. Maybe that may be the reason why single source principle is not considered in this book. And yeah, as you said, there are some other books they have considered where that plays single source principle. I think maybe like in time goes, we will be getting like a clear answer on that.
Yes. I agree with you.
Dr. Nalin, it was very interesting to see you some slides on this derivation of the material parameters from the field test. Actually, we have not gone into deep into that. I won't have a look on this this part 2 of the code. So you said in Sri Lanka we don't. I fully agree because we don't follow the site investigation guideline and we don't do required number of testing. So this can you a little bit elaborate on this cautious estimate? Any idea like? Is it what you mean is like we get the values and we make an educated judgment based on the experience?
Exactly. That is what I wanted to say. It is.
Okay.
Yes. It's based on the judgment.
Okay.
I mean, we can't generalize any other procedure for obtaining these design parameters from the derived values. It's very dangerous. I think generalizing.
Dr. Nalin, this is only for your information. I was contacted by one of actually he visited Sri Lanka some time back from Romania, Dr. Mirja, and he contacted me recently and he gave me a kind of a shocking news. There was a Eurocode 7 workshop recently in one of the European countries, and he said they are going to further revise this code. I don't know, maybe they are going to remove these combinations. I'm not sure, but we are also following. He said to me something like that. But I didn't see anything like that in the
I heard that they are going to introduce some revision in 2022.
Maybe.
I think it got delayed due to COVID. Maybe they are planning to do it earlier, but due to COVID issue, it has been postponed. I heard that they are going to do a revision in 2022 or 23.
Yeah, I think the main reason, Dr. Nalin, is now compared to the BS code, here there are, if you see including combination 1 and 2, there are 4 combinations. So it is more complicated, and I think they feel it's quite complicated. So I think maybe they want to simplify. In Singapore, I checked with some of my friends. Singapore, they are using mainly design approach 1 only.
Okay.
Yeah. But as you said, it depends, no? Like depending on the design and the design situation.
Yes.
Other questions from our participants today? So you can share your practical knowledge in these areas.
I just wanted to, just one suggestion for hosting, the Zoom sessions. There is an option in the Zoom where you can mute the audience. They need a permission to unmute during the session. That will be good because when people enter, I think the microphone is on. Sometimes it disturb the speaker also. So I would suggest there is an option in the Zoom where you can mute all the participants while the session is on. Only they can unmute during the discussion session. You may consider that one in your future presentations. Yeah, thanks.
So with that note, there was a request to share the presentation. Generally, we upload the presentation to our section committee YouTube channel. And also, you can subscribe and get the presentation later. There are many presentations we have already uploaded in this YouTube channel. So with this note, Dr. Nalin, shall we wind up today's presentation? I take this opportunity again. Thank you. Thank the very interesting, informative, and practical presentation. Really well for all members here. And we have joining, I think, members from Sri Lanka, overseas, and thank you very much for all your presence here this evening. And we'll meet with another presentation in the near future from Civil Section Committee ISM. And thank you again, and good night, all of you.
Thank you very much for having me, Engineer Manjula. Thank you very much.
Thank you, Dr. Nalin. Good night.
Good night. Good night, Dr. Nasir.
Thank you very much.